All right. I'd like to start this class by reminding you an example that we did earlier, back in chapter 1, when we were defining probability spaces for the first time. Do you remember the following example? Let me try to find it here in the notes. I start driving to work every day at some randomly chosen time from 8 a.m. to 8:30. Let me try to find that. Here it is. I start driving to work in the morning at some time uniformly chosen in the interval from 8:30 to 9. Okay? What is the probability that I start driving before 8:45? Do you remember this example? Right. And there's a radio program that starts precisely at 8:30. And it lasts anywhere from 5 to 15 minutes. What is the probability that I catch at least part of the show in the car? Okay, so this is the example. Let me try to make it larger. So let's see. This is it. So this was the first example of a continuous sample space that we studied. Okay? I start driving to work at some time uniformly chosen from 8:30 to 9. Okay? What is the probability that I start driving before 8:45? How did we answer that question previously? Do you remember? By intuition. Okay, we said this is our sample space. Okay, 8:30 to 9. It's a continuous sample space. And the event of interest is this first half. The event of interest, event A, consists of the first half of this sample space. Exactly half of all the points in the interval are included in my event A. So the probability of A was computed as 1/2. Right. Now, what if I wanted to define a random variable here? What if I wanted to define x as my start time? My starting time. Okay. Let's define this, if you want, as my starting time in minutes after 8:30. Okay, so what can you say about x, the random variable x? Is x positive? So x is positive, and what is the range of x? X lives between, x is in 0 to, well, it's how many minutes, x is how many minutes after 8:30 I start driving. So x is in between 0 to 30 minutes. Okay? If x is 0, it means I start at 8:30. If x is 15, it means I start here. If x is 30, it means I start at 9. Okay. What kind of a random variable is x? It's different from the discrete random variables we studied so far, right? If you wanted to come up with a probability mass function for x, could you do that? What is the probability that x is equal to 0.3, for example? what is the probability that x is equal to 15? What do you think?
Surface area.
What do you think? Can x be exactly 15? Yes, it can. Okay, but what is the probability of this with respect to this? Do you think they are equal? They are equal. Okay, they are equal. Okay, they are equal. Suppose they are just a constant. For every value, it's a constant. Then what would happen? What is the probability that x is between 0 and 30? That will be the sum of all those values. How can it be 1 if all these values are different from 0? Integrating what? You're really thinking in the right way. You're integrating something, but what? Okay, let's think a little bit more. Huh? That's all the right intuition. Okay, so let's think a little bit more. So we want this to be 1, which makes a lot of sense. What's your name from section 4? Yes? Necati. Okay. So Necati, do you agree with this being 1? Okay. What do you think this is, Necati? 1 over 2. Why? By symmetry. Essentially, here's what we're thinking about. We're saying here is 0, here is 30, okay, and we have a constant level of probability per minute, okay, probability per minute, and this is x in minutes, and the probability of x being less than or equal to 15 is this area. Okay. The whole area should be 1. Okay. So the level of probability per minute, in a way, probability per unit distance here, should be 1 over 30. That's the intuition we have. Okay? We will call that a probability density. Okay? We will say this is Px of x. The probability density function. Probability density function is like a derivative of probability. The more probability density you integrate, the more probability builds up. Okay, so let's switch to the new topic of the day. Let's go to page number 57. Okay. Oops. Okay. So the topic is continuous random variables. X here is a continuous random variable. It takes values from real numbers, just like our discrete random variables also are able to take values in real numbers. However, the difference here is that X takes a continuum of values, and we cannot associate a probability mass with the values that X takes. If we try to associate a probability mass here, we would be in trouble. In fact, let me ask you something. Oh, okay, I'll ask you that later on. Let's first make this definition. A random variable X is continuous if there is a non-negative function fx called the probability density function, or PDF, such that the probability that x is in this region B is found by integrating over B fx of x dx. Okay? So let me write it down. The probability that x is in area A, in the region A, is the integral over A fx of x dx. So in our particular region, if this is our region A, between 0 to 15, then we are integrating from 0 to 15, 1 over 30 dx. Okay? And this gives us 15 divided by 30, which is 1 over 2. Okay? And the level, let's call this fx of x. The level here should be 1 over 30 in our example. Okay? So let me repeat. We found the probability that x is between 0 to 15 by integrating from 0 to 15 the density function. Okay? And that gave us the obvious answer, 1/2. Okay? Now, in general, the probability that x lives between A and B can be found by integrating from A to B the density function. Okay? Which is the area under the graph of the PDF. Every continuous random variable has a PDF. So answer me this question. What is the probability that x here takes the value 0.3? We can find this using this equation, right? Integrate from, what is A? 0.3. What is B? 0.3. Okay, to the density, 1 over 30 dx, which is what? 0. Okay, so the probability that x is exactly 0.3 is 0. How about the probability that x is exactly 15? That's also 0. So the probability that x is any particular value exactly is 0. Does that mean it's impossible for me to start exactly at 8:45? It's not impossible, but it's an event with 0 probability. Okay? So there's a difference. Okay? So you will see examples of that again, so better get used to it. Now, a random variable x is continuous, as I said, if and only if there's a PDF. So let's understand what kind of function this PDF has to be. Okay? First of all, we find probabilities by integrating PDF, and we need to be able to integrate over any arbitrary region, and that should give us a probability. But we know that probabilities are positive. Okay? Since probabilities are positive, the density function also has to be non-negative. Okay? I mean, probabilities are non-negative, so density function has to be non-negative. Okay? Because if it went negative over any region, you could integrate over that region, however small that is, and get a negative probability, which wouldn't make sense. Okay, so density functions are non-negative. Normalization property. Density functions should normalize somehow. What do you think that property should say? Normalization. Normalization is, in this setting, area under should be equal to something. Integral fx of x dx. Now, since this is probability per x, probability density, if you integrate over negative infinity to infinity, okay, that would mean what? That would mean the random variable x takes values between negative infinity to positive infinity. But that's a certain event. Why? Because the random variable x is a real value, so it has to live between negative infinity to infinity. So this should be 1. Any problem? Okay. And maybe the third one is sort of more important because it's less obvious. Let's think of very small delta, very small values of real number delta. Think of the probability that x is between script x and script x plus delta. Okay, so we can say, okay, suppose this is the probability density function fx of x. And I have script x here and script x plus delta here. Suppose this is a very small interval. Now I'm thinking about the integral here, the area under the curve right here. That is the integral from x to x plus delta fx of a dA. Okay, let's use a here. Okay. Now, as delta goes to 0, okay, as delta becomes arbitrarily large, this becomes arbitrarily close to something. What is that? This area becomes approximable by, what is this value? This is fx of script x, and this value is fx of script x plus delta. Okay? So this area is roughly fx of x times delta. Okay? Area of the rectangle. Okay? Approximating it by a rectangle. You know this argument from the Riemann integral. Okay? So basically, this gives us an intuition about what density is. The density, sorry about my very skewed lines, but you understand. This is probability per unit length. Okay? So the probability that the random variable x is roughly around script x is proportional to the density at that point. Okay? So the density indicates the intensity of probability at that point. Okay? So you can also view it as probability mass per unit length near x. Okay, that's a good definition, intuitive definition to have. Okay? So now that's it. It's non-negative. It integrates to 1. And it sort of gives us probability mass per unit length, okay, near the point that it's evaluated at. That's all that density has to satisfy. Okay? The density itself may be larger than 1. Let's see an example. Okay? Okay. So please look at this example. Fx of x may be larger than 1 sometimes because fx of x is not a probability. Okay? So fx of x is cx squared when x is between 0 and 1 and 0 otherwise. Let's plot that. So as a function of x, here is fx of x. Now, what is its value at 0? it's 0 at 0. At 1, it is c times x squared, which is c itself. Now, let's find the value of c. Okay. Let's find the value of c. What do you think c is? Let's use the normalization property. Fx of x dx, x from negative infinity to infinity, should be 1. Right? So cx squared dx, x from 0 to 1. Okay. Should be 1. What is this? This is c times 1 over 3. Okay. So this tells us that c should be 3. Okay. So the value of c here is 3. Okay, this shows us that densities can be bigger than 1. Okay, they're not probabilities. Okay, any questions? Okay, can densities go to infinity, do you think? Okay, provided they don't go to infinity everywhere, right? If they go to infinity over a manageable region such that their integral is finite. Okay, then before answering that, let's answer this question. For this example, what is the probability that x squared is less than 0.5? Why? How do you know? Can you compute it? Okay, let's compute that. The probability that x squared is less than or equal to 0.5. Okay, what do? We integrate fx of x dx, the probability density function, over this region, x squared is less than or equal to 0.5. Okay, let's say x such that x squared, absolute value squared, is less than or equal to 0.5. Well, what is that region? That region is negative 1 over, negative square, what is this, 1/2, negative 1 over square root of 2 to positive 1 over square root of 2, right? Fx of x dx, but fx of x is 0 before 0. So we need to only integrate from 0 to 1 over square root of 2, 3x squared dx. Okay? And that gives us x cubed from 1 over square root of 2 to 0, which is what? 1 over 2 square root 2. Okay? Is this clear? So, any questions up to this point? Is it clear up to this point? Okay. So, let's address the next question. Can a PDF go to infinity? Yes, it can. Here's an example. Fx of x, in the example, is c over square root of x. There's a typo in this view graph. In your notes, it's corrected. Let me write the correct one here. Fx of x is c over square root of x. In fact, it's not a typo, but I changed the example today. When x in absolute value is is less than or equal to 2 and 0 otherwise. Okay? So how would this look if we plot it? First of all, the PDF fx of x takes values only from -2 to +2. At 0, what happens? It goes to infinity. So how does it go? Just like this? Okay, so let me try to... At -2, what is the value? Well, we don't know before computing c, right? Can someone quickly compute c? Okay, compute c as an exercise. Okay, and show for what value of c the area under this curve is equal to 1. Right. It just goes to infinity. The value. Mm-hmm. Mm-hmm. Oh, I'm sorry. Here, I made another typo. Right. It's like this. Yes. So it's either like this, as in the example, or like this. Thank you for fixing this typo. Okay? So let me rewrite this. Square root of absolute value of x. Okay, any questions? So pick either version of the example, either as in the view graph or here. Okay? But don't mix the two, like I did. Okay, so what's next? Now, the final thing we'll do today is give a name to the PDF in the example that I started with today, which is I set out sometime uniformly chosen from 8:30 to 9. What does that mean? Uniformly chosen. Okay. Uniformly chosen means x comes from a uniform PDF. So in your handouts, you will see a graph of the uniform PDF. Okay. You already know the discrete uniform PMF. Okay. It takes equally, it takes values in a range A to B equally probably. Okay. The continuous version is simply the continuous version. Okay. So a PDF is uniform between A to B if it's basically constant and equal to 1 over B minus A between A and B and 0 otherwise. Okay? What's the difference here? In the PMF case, we had B minus A plus 1 because we had exactly B minus A plus 1 values. Here we're working with a continuous range between point A to point B, and the distance is exactly equal to B minus A. So to normalize, we're dividing 1 by B minus A. So let me quickly sketch that. Fx of x is between A and B equal to 1 over B minus A. It's the simplest distribution. All values between A and B are equally likely, okay? And any interval, the probability that x falls into any interval is given by, is proportional to the distance, the proportion to the length of this interval, right? Why? Because the probability, so let this be an interval y to z. Okay? What is the probability that x is in between y and z? Okay, let's do this. What is that probability? It's the integral from y to z, 1 over b minus a, okay, dx. Okay, which is simply what? Z minus y divided by b minus a. In other words, the ratio of this length over the whole length. That is why the probability that I leave home before 8:45 in the example is 1/2. Right? Okay. So that's the uniform random variable. The Gaussian. Okay, there's a big transition from the uniform to the Gaussian. So brace yourself. Okay? This is the Gaussian. Okay? Now, the Gaussian is one of the most common distributions in life, in engineering, and in other fields. Okay? It may look scary to you at first, and it may look scary to you maybe later on, but it has a really nice graph. Okay? So let me try to sketch that. Okay, so let's say this was uniform, and this is Gaussian. Let me write the PDF first. Fx of x equals 1 over square root 2 pi sigma squared e to the minus x minus mu squared divided by 2 sigma squared. So what is this sigma and mu? How many parameters do you see in this equation? 2 parameters. What are they? Sigma and mu. Sigma squared maybe and mu. What do you think sigma squared is? Sigma squared, we've seen this letter before. Variance. Sigma is the standard deviation. Sigma squared is the variance. So that's nice. At least the variance comes together with the PDF. Okay. What is mu? Do you think? Mu is the expectation. This is the expectation or the mean. Sigma squared is the variance. So sigma is the standard deviation. Okay, so this is just a function. It's a function of a particular shape. What kind of shape does it have? Bell-shaped. It has a bell curve shape. Okay. The mu and the sigma control where it is, where it makes a peak, and how fat or slim it is. Okay. So in particular, it's centered at mu, which makes sense. The center of gravity of the distribution is at mu, which is the expectation. And the standard deviation, remember, controls how spread out the distribution is. This wideness is controlled by the standard deviation. Okay? So the larger the sigma, the wider spread the curve. Okay? What happens as sigma goes to 0? It goes to a constant. So this curve gets narrower and narrower and eventually goes to an impulse. Okay? So that gives you a hint of what the PDF of a constant should be like. Okay? So a constant takes, if a random variable takes the value c with probability 1, then what should be the density at that value? Well, when you integrate the density around c in an interval of length 0, you should get 1. How is that possible? That's only possible with an impulse. Right. In this course, we're not going to use impulses. but it is possible. It is possible to go from densities to PMFs and represent PMFs as impulses right at the discrete points where the random variable takes those values. Okay, so anyway, this is the Gaussian, and I'm happy to introduce you to it. Most of you will use it in the rest of your life. Okay. Finally, here's my favorite. It's the exponential random variable. Why is it my favorite, do you think? The main reason is I work on networks. Okay? And it's very useful in my area of interest, exponential distributions. And secondly, it has a lot of nice properties. So here's the density. Actually, I don't like knowing the exponential by its density. I like knowing the exponential in some other way. But let me draw it, sketch it for you. Okay. So it goes like this. What is its value at 0? It's lambda. Now, lambda controls how fast this curve decays. So in your handouts, you have fx of x plotted you have fx of x plotted, let me see, for two different values. There you go. And now, can you read for me which values those are? Lambda equals? Okay, so lambda equals 0.5. Let's see. 0.5 looks something like this, suppose. How about lambda equals 2? Let me redraw these. Okay? Lambda equals 0.5 and lambda equals 2. Okay? The 0.5 curve starts here and decays slowly, whereas the lambda equals 2 curve starts here and decays much faster. Okay? Now, as I said, I don't like knowing the exponential this way. I like to know the following. I like to know the probability that x is bigger than or equal to a. Okay? The probability, or let's say x is bigger than a. Let's find the probability that x is bigger than a if a is exponential. Okay, this is the integral from what to what? From a to infinity. A to infinity, fx of x dx. So take an a, integrate from a to infinity. Okay? What do you get? From a to infinity, lambda e to the minus lambda x dx. You get e to the minus lambda a, provided a is positive, right? Okay. If a is negative, what do you get? 1. Right? You would get 1 if a is less than or equal to 0. Okay? Because then you are integrating the whole PDF, I'm sorry. Now, I like to exactly know this. This is how I define an exponential random variable. The probability that x is bigger than a decays exponentially with a when a is positive or 0. And the rate of decay is controlled by lambda. The bigger the lambda, the faster the decay. This is what I suggest you remember about the exponential random variable. Okay? Okay? So we learned three continuous distributions. The uniform, which is just constant in an interval, equally likely values. The Gaussian, which takes all values actually from negative infinity to infinity, but it's really centered around a mu. Okay? And finally, the exponential, which is one-sided. It takes values from 0 to infinity, but it's really more concentrated around 0. And how concentrated around 0 it is controlled by this parameter lambda. Okay? So, for example, if the lifetime of a certain photon is exponentially distributed, and its rate, lambda, is 1 over 10 to the minus 3 second to the minus 1, okay? Its mean lifetime would be 10 to the minus 3 seconds. The mean of the exponential distribution is 1 over lambda, which makes sense, because the larger the lambda, the smaller the expectation. Because the larger the lambda, the more concentrated it is around 0. Okay? This is very useful in modeling the lifetimes of things like this that are expected to be small. Okay, so that brings us to the end of this hour. I'll see you next time.